Hello, Nikolai. How are you? Can you hear me? Hello.
Belum dengar sepertinya, Pak.
Yeah.
Nikolai, how are you?
Halo. Assalamualaikum Pak Wisnu, Pak Jarot, Pak.
Pak
Pak Seaborg, Pak Rohadi.
Ya, Assalamualaikum Mas Sidik. Terima kasih nih Pak Sidik waktunya menyempatkan hadir. Terima kasih Pak Jarot, Pak Seaborg.
Gimana nih? Hello,
Nikolai.
Can you hear us?
Let's try again.
Yeah, hello. Good morning.
Now I hear you. Good morning. Good afternoon, Jared.
Well, let me introduce our boss. First, Dr. Rohadi Awaludin is the chairman of research organization of nuclear technology, nuclear energy, and then Dr. Saiful Bahri is my direct boss. So he's the director of the nuclear fuel cycle and radioactive waste research technology.
Fantastic. Great pleasure to meet both of you.
Okay.
Nice to meet you too as well, Nikolai.
Nice to meet you.
Sorry for the time because it is early in the morning in Copenhagen.
It's okay. This is a good time.
Yes.
Okay.
You had a discussion forum, or was it Barberton? There was a day where you had a focus group discussion which started at 2:30 a.m. Danish time. That was a little early.
Oh, really? Okay. Okay.
This is okay.
Okay. Pak Saiful, can we start or?
Yep, Mbak Nisa. I'll try a newcomer right now, Pak Jarot, to be the master of ceremony right now.
Okay, please.
Our new fresh employer as well. Ya, silahkan Mbak Nisa.
Selamat siang, Bapak, Ibu. Bismillahirrahmanirrahim. First of all, ladies and gentlemen, please be sure to turn off your microphone as the agenda about to begin. Thank you. The Honorable Head of Business Development Seaborg, Mr. Nicholas Agerhaman, Chairman of Organization for Nuclear Energy, Mr. Rohadi Awaludin, Head of Research Center for Nuclear Fuel Cycle and Radioactive Waste Technology, Mr. Saiful Bahri, Mr. Sidik Permana from Bandung Institute of Technology, Mr. Azizul Hakim from National Research and Innovation Agency, and all participants. Good afternoon and Assalamualaikum warahmatullahi wabarakatuh. Thank you for joining us today on this forum group discussion, Seaborg Compact Molten Salt Reactor, Fuel and Waste Treatment Technology as a collaboration between the Center for Nuclear Fuel Cycle and Radioactive Waste, BRIN, and Seaborg. My name is Anissa Isnaini and I will be your MC today. Ladies and gentlemen, as we know, a compact molten salt reactor, or CMSR, is a type of nuclear reactor that uses liquid fuel instead of solid fuel. One of the key advantages of CMSR is its ability to operate at higher temperature than solid fuel reactors. This means that it can generate more power per unit of fuel, making it more efficient. Yeah. But there are also some challenges associated with the CMSR. One of the main challenges is the need to develop new materials that can withstand the high temperatures and corrosive nature of the liquid fuel. Today, we will talk about the fuel and radioactive waste management of Seaborg molten salt. But before we start the agenda, at first we will sing the national anthem of Indonesia. Thank you. Move to the next session. I would like to invite the Chairman of Research Organization of Nuclear Energy, Mr. Rohadi Awaludin, to give opening remarks and also open this forum group discussion.
Can you hear my voice, Mbak Nisa?
Yes.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, our colleagues in Jakarta, and good morning for our colleagues in Denmark. First of all, I would like to thank Mr. Nikolai Eckerhamann from Seaborg. Thank you very much for your time and your give explanation and sharing about compact molten salt reactor to our colleague here in Indonesia. Thank you very much for your valuable time. And I would like to thank Pak Sidik Permana. Terima kasih Pak Sidik for your time and your response and comments. I believe it will be very useful for us here in this one session about nuclear energy. And thank you, Pak Jarod, for your participation today. Ladies and gentlemen, as we know that Indonesia has decided a target that we will be net zero emission in 2060. So we believe that nuclear energy will be used in supplying our energy in Indonesia. So now Ministry of Energy and Mineral Resources discussing some roadmap, discussing how to achieve the net zero emission. And maybe some of participants knows that now one of the roadmap is that nuclear energy will be used about 5 to 7 gigawatt in 2049 and 35 megawatt in 2060. But I believe that it's too late. I believe that the introduction of nuclear power plant must be earlier than 2049. So hopefully in 2040, for example. So to achieve the target, so we are here in Nuclear Energy Research Organization must be ready to support the government program in introducing nuclear power plant in Indonesia. And maybe government will start with experiment power plant, but maybe we'll start with directly to commercial power plant. We have to be ready to support the program of the government to achieve net zero emission and to introduce nuclear power plant in Indonesia. And today, I think it's a very good opportunity for us to have our guest speakers from Seaborg Technology that will share about a new technology, a nuclear power plant, compact molten salt reactor technology. I think it's also new for us here in Indonesia, and it's will be very potential and very advanced nuclear power plant. I think it has a compact size, high efficiency, and ability to operate at high temperature that make it an attractive option for the generation of clean and reliable energy. And so we also, to prepare our capacity in supporting the government, we have to increase our collaboration with many stakeholders, nuclear energy in Indonesia and also from foreign countries, I think. So I think it's a very good opportunity for us to learn, to increase, to expand our cooperation with foreign countries. And finally, last but not least, I would like to thank Pak Saiful Bahri and team from the Research Center for Fuel Cycle and Product Waste for preparing and co-organizing this event with Seaborg Technology. And by saying Bismillahirrahmanirrahim, I declare that this discussion is open officially. Thank you very much for your attention and cooperation. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Rohadi. Ladies and gentlemen, after this opening ceremony, we will go directly to the main agenda. This section will be hosted by Dr. Saiful Bahri as a moderator. Dr. Saiful Bahri, time is yours.
Terima kasih, Mbak Anissa. Kedengaran suara saya, Mbak Anissa, ya? Can you hear my voice? Yeah.
Yes, clearly.
Thank you so much. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everybody. Distinguished head of nuclear energy research organizations, Dr. Hadi Awaludin, distinguished speaker today, Nikolai Eger-Hammond, and other colleague here from BRINS, from PLN. We have several participants, really diverse participants, I think, from the company, industry, university, as well as from our research organization, from the Center of Nuclear Fuel Cycle and Radioactive Waste Technology. Before we begin, allow me to a little bit read the curriculum vitae of Nikolai Eger-Hammond. Try to share his curriculum vitae. Yes. Yes. Kelihatan nggak, Mbak?
Terlihat, Pak.
Lihat ya, baik. Oke.
Oke, Pak. Oke.
Yes, right. Mr. Nikolai Eger-Hammond is graduated. Actually, his education is finance and strategic management. I think it's quite interesting. I think for the one who's really involved in nuclear engineering and nuclear energies, but have a background from finance and strategic management. And his employment history right now is the head of business development Seaborg, and also 2021 until 2022, the director of project development Copenhagen Energy. And from 2020 until 2021, the director of project development Denmark offshore wind power. It's also interesting. You are from the renewable guy and then change it to nuclear people, nuclear engineer over there. And 2019 until 2020, the director of TSA warranty management and SWA is from wind power as well. And the main relevant point and achievement here. So many here. Probably we can share. Perhaps the audience interested to read one by one, or later on, probably Nikolai like to highlight a few here and there. Probably a few industry here come in with us, interested to cooperate in one or two several area you've been mastered or you've been expert in here. Okay, ladies and gentlemen, there's a little bit information about Nikolai Egerhamans, and without further ado, like Mr. Rohadi said, that this forum group discussions, it's really beneficial for us, for industry, for research organization, and for universities to really prepare for the future of net zero emissions, to tackle the net zero emission by preparing nuclear power plant. Whatever the nuclear power plant have sort of a direct deployment from the, let's say, the available market right now, or for example, through the development of demo plant, for example, sort of like that. And for us as a research organization, it's also for our colleagues from university. Yes, I think this event is very good to really get better understanding what is the technology of compact molten salt reactor, as well as try to find the gap or study how to really familiarize this technology. So whatever this technology coming to Indonesia, we are ready, and perhaps we can also try to contribute this kind of technology for further development or for further deployment in Indonesia. So Nikolai, I will give you probably 40 or 50 minutes or whatever, whatever is comfortable for you, and you can start from now, and the floor is yours.
Thank you very much, Mr. Bakri, and thank you to Jared and the BRIN organization for hosting this. Thank you, Anissa, for a good introduction, and Rohadi Awaludin, thank you for having me. So, of course, we really appreciate the opportunity here from Seaborg to present our technology to you and have this discussion around how we would fit in Indonesia and potentially the collaboration between BRIN and Seaborg. As was already mentioned, I have a background in finance and have had a large part of my professional career in renewable energy. I've been in offshore wind for almost a decade, and I think so while I'm not the one actually developing the technology in Seaborg, we have a long range of engineers and PhDs who are specialists in that field. I am the one responsible for commercializing it, and I think a lot of the experiences from the renewable industry are relevant to the small modular reactor space in nuclear, because a lot of what has happened in the renewable energy industry for the last 10 years will have to happen in the small modular reactor industry if we are actually to have success. But I can probably come back to that. So today I brought a general presentation of Seaborg, and I'll run through that, but then I'll also invite questions as we go along. I'll be very happy to have it as a dialogue, and yeah, should you, I'm not sure if I'm sharing the right screen, just a second. Do you see a screen in presentation mode? No, you don't, right?
Yes, we can see BRIN, Seaborg BRIN presentation.
Okay, good. Fantastic. Yes, so I'll run through the standard presentation, and then the topic of today is on the fuel cycle and the waste management. I'd love to have a more dialogue part on that, because truth be told, that is something in the molten salt space that needs development and collaboration. So let's dive into it. Starting out with who Seaborg is. So we are a Danish company. We were founded in 2014. We are so far privately funded and therefore also privately held. That means that we are free to operate wherever we want and however we want, as long as we abide to the international rules. We are some 120 employees by now from 25 nationalities, and around 20 to 25 of these are PhDs within chemistry or nuclear physics and so on. Our headquarters is in Copenhagen, Denmark, where I'm also located, but we also have offices in South Korea and in Singapore. We are developing our technology together with Samsung Heavy Industries from South Korea and together with Korea Hydro and Nuclear Power, who both of them, of course, bring a lot of industrial and nuclear experience, which is critical to the Seaborg journey. As has already been pointed to, our product is a compact molten salt reactor. That is the image to the left. The key features of it is that it's relatively small compared to a nuclear reactor. It is made primarily from industrially available products and components. So we are, right from the beginning, leveraging scale economies and industrial efficiencies, and also industrial quality and predictability, all of which are great features in a nuclear setting, and something makes us believe that this is a product that has a lot of viability in the market. We envision that it would be deployed on barge structures, so floating non-self-propelled structures, as shown in the bottom. It can be put together either with 2 reactors, creating 200 megawatt of electricity, or it can be 4 reactors doing 400 megawatt, 6 doing 600, or 8 reactors as the largest barge, producing equivalent of 800 megawatt electricity. As it is nuclear, we like to highlight that there is no reason not to believe that it will be at least on par with the nuclear industry in terms of capacity factor. This is, of course, interesting also in an Indonesian setting where most of the other zero emission sources, such as wind and solar, they are running with capacity factors significantly below this level. And then, as was mentioned, the compact molten salt reactor, one of the key benefits of this is that the uranium is dissolved in salt, and thanks to the properties of the salt, a lot of the worst case scenarios imaginable for a conventional nuclear reactor cannot happen in a molten salt reactor, because there's no water within the reactor, and therefore it operates at near atmospheric pressure. As you are probably all very well aware, but we like to remind our audiences, molten salt reactors are not new per se. It's a concept derived from the US. It was first launched in 1954, operated for a few weeks, obviously a little bit of run-up before that, but was later shut down as a research in the US, and now has been picked up by several commercial players, one of them being Seaborg. But one of the features that many previous tries in the molten salt space have been struggling with is that the graphite has been used as the moderator. And what they have seen is that the moderator is cracking under radiation, and this is where we have tried, we are doing something different. We have patented a moderator solution where we then don't need graphite within the reactor core, and that is also one of the reasons why we have a unique compactness of our reactor compared to the graphite moderated reactors. Now, since this is, and then our solution is that we use natrium hydroxide as the moderator in a design as shown in the top left-hand corner of this slide. So with steel tubes that we call fuel tubes, within which we have the fuel salt. So that's the salt containing the enriched uranium. And around the tubes, you have the sodium hydroxide, so the moderator. And as many of you will appreciate, the sodium hydroxide is a more efficient moderator than graphite. So we will need a lower volume of natrium hydroxide to have the same moderation as if it was graphite. So that's the reason why we can do it so compact. This idea of using sodium hydroxide is good for the new neutronics and for the moderation, but of course, as also mentioned before, introduces a new corrosion issue because sodium hydroxide is also highly corrosive and is corrosive in a slightly different way compared to the fuel salt. So now we have steel tubes that are exposed to two different types of corrosion. And that is where Seaborg is doing the primary part of our proprietary development that is within the chemistry control. So we have developed a chemistry control unit that in rough terms looks like on the left. And this is this unit is the one responsible for keeping the chemistry within the reactor in a condition where we believe we can control the corrosion so that we have the longevity we need of the reactor core. This technology has also actually allowed us to make a sister company, which we call HYME, so HYME. The HYME solution is one that builds on solely using sodium hydroxide and using it as a thermal heat storage. So we make big tanks of sodium hydroxide with conventional heat exchangers, so taking electricity and generating it to heat, and then storing that heat within the sodium hydroxide, which is very efficient. There's a very large thermal capacity in the sodium, so it's relatively compact and it's very cheap to source sodium. So overall, it's a relatively cheap system. And then, of course, the heat is transferred back to electricity via heat exchangers to water and then a steam turbine. But it's just to say, so we're utilizing the same portfolio of patents in two different technologies, both in Seaborg, our nuclear arm, and in HYME, our thermal storage element, which allows us to benefit from experiences of both companies building on the same portfolio of IP. See that there's a question in the chat. Not for me. Good. So in a simple schematics, this is how the reactor will work, or the nuclear power plant actually as a whole. So you have the lighter green color tubes. That's the fuel salt, so the one with the enriched uranium that is circulated through the reactor core, where you have the moderator shown as the dark green color here. Within the reactor core, the moderation allows the fission process to go critical and remain critical, and then the enriched salt is pumped through the system, heating up through that cycle, and then pumped out of the reactor core over to a primary heat exchanger, where the heat is transferred from the enriched salt to a salt with no radioactivity in it. So a clean salt, if you will. And then that salt is pumped over to another heat exchanger, which is in the steam generator, where we create steam that can drive a steam turbine. The concept we use for passive safety is the concept of drain tanks. So in the event of something unexpected, our system is designed with so-called drain tanks, with big jars that can contain the salts. So once drained, the salts are in an environment where the fission process is not critical, and therefore that it will be automatically cooled. These drain tanks, by the way, are passively cooled. So you would have what you would call walk-away safety, in the sense that no operator interaction is needed while the salt is in the drain tank. Yeah. In a slightly more real-life graphic, this is how we envision the product. So on a barge, the concept is that the barge will come with two reactors ready to operate. That's on the front of the barge in this schematic. The reactors will generate the heat that is transferred to the boiler, and then a steam turbine is shown in the middle. And then that in essence is what we call a power module. So such 2 reactors will deliver equivalent of 200 megawatt electrical. The vessel will also come with 2 empty compartments, and that is to cater for after the first fuel cycle has burned out, we will deliver 2 new reactors with new fuel, and then those will operate for 12 more years. Yeah, and as shown as in the top right-hand corner, then those fuel or power modules can be replicated. So an 800 megawatt barge would have then 4 of these modules. Exactly the same logic, just 4 of the modules. And then in the bottom right-hand corner, that's where we've shown the reactor and with the drain tanks underneath, the steel container in the bottom of that schematic is the drain tank. And the reactor core will be encapsulated by shielding, of course, and then water for both protection and further shielding, and then the steel structure of the vessel. So all in all, a well-protected system, and only the reactor core itself will be activated during operations, and then of course the shielding. Our concept, as mentioned, we're working together with Samsung Heavy Industries. They will be the ones we envision will build at least the first couple of barges, and then from Korea we'll export the barges. So once commissioned outside of the Samsung yard and proven ready to operate, it will be towed to wherever the permanent site of production will be. That could be Indonesia, that could also be Denmark or countries elsewhere in the world. The logic is to have a standardized and modular production method to minimize cost and increase predictability and reliability. Key challenges for the conventional nuclear industry. Doing this requires that we rethink the licensing process, since there is no world yet that has a licensing framework for floating advanced nuclear reactors. So we are posing 2 challenges to most regulatory frameworks. One, that we are an advanced, so a molten salt reactor, and the other that we envision to be on a barge. The good news is that there are known solutions to deal with some of those challenges, and we hope to rely on those. So the first one is the floating element. The IMO, the International Maritime Organization, is a long-standing UN organization governing essentially all seagoing vessels. And those vessels are classified through classification societies. And here, ABS is the American Bureau of Shipping. So that is a classification society. You also have Lloyd's Register and DNV and others who are doing a similar job. So essentially what they are doing is they are taking a design of a vessel and holding that against the rules and regulations from the IMO. And then they classify that the vessel is abiding to those rules and regulations. Once the classification society has classified the vessel, then it's the flag state. In the maritime space, it's the flag state who's responsible for ensuring that the vessel lives up to its classification in terms of periodic reviews and maintenance and so on. But of course, that alone is not sufficient for a nuclear vessel. So that's why we also have the IAEA in this UN authorities box in the top. The IAEA have guidelines for nuclear reactors and also some emerging for molten salt reactors. And these guidelines are then also taken into our work with ABS, the American Bureau of Shipping, when classifying our power barge. So the classification that we will ultimately receive from ABS both confirms the vessel structure, but also the nuclear technology, so that the classification of the ship is jointly both a vessel, a seagoing, seaworthiness classification, and a nuclear safety classification. This will make a barge which we believe is safe and ready to be deployed. But of course, we cannot just deploy a nuclear power barge because we think it's safe. the local regulators will also need to approve it. And this is where we believe that this model can help. For example, the Babaten, Brin, in this case, in Indonesia, as they can rely on the classification work already done by ABS. So instead of having to do a full review, they can lean on what ABS has done in terms of structural strengths and appropriateness of design, and then focus on probably the nuclear aspects that are of higher interest and relevance in the review. We believe in Seaborg that this will allow for a faster review of new technologies and also then a faster and safe deployment. Once the power barge is deployed, of course, we are still subject to safeguard inspections and to local regulations and inspections as any other nuclear power plant would be. Only major difference is we will be still in the sea. One of the features that we are working on is that we are working with competent nuclear regulators as it is today, in that we call our global licensing partners. These are to help us in the approval process of our power barge technology, but also they will have to help us scope what changes to regulations are required to allow for a floating advanced nuclear power barge. And whatever learnings they have agreed that we can then take out to, for example, Indonesia and share for Indonesia's consideration when developing your regulations around a floating nuclear power barge. So all in all, we believe that this is a well thought through licensing process that will allow for, in a nuclear sense, fast deployment. And of course, the main interest is to be compliant with rules and regulations and international guidelines, and to deliver a safe product before anything else. And then, of course, if it's fast and reasonable in the burden on the regulators, then that's also a plus. But the safety and the compliance are the two first priorities. Then just a few words on the American Bureau of Shipping. You probably know them, but it's just they are an international classification society with a long-standing track record, both in the maritime, but actually also in the nuclear space. The process that we have been working through, they've reviewed our reactor core design, giving us this feasibility approval. It's like an initial step, and that is was the kickoff of our process, where we are now working towards first a prototyping a couple of years from now, and then full scale towards the end of the 2020s. Hopefully having commercial deployment in 28, 29. And then probably more specifically to the theme of the discussion forum today, we have the life cycle of the barge. As I mentioned, we come with 2 live reactors. The fuel, when transported, are in the drain tanks. The drain tanks are heated, pumped back to the reactors, and then operation starts. 12 years later, come with a new set of reactors with new fuel, and we can operate for another 12 years. The 2 spent reactors, or the reactors with the spent fuel, the fuel will be drained to the drain tanks, but the reactors will stay in the power barge, so that there is no handling of spent fuel within the lifetime of the power barge. Then after another 12 years, so 24 years combined, the barge with the 4 burned out reactors and the spent fuel in the drain tanks can be towed away from the production site to a decommissioning site. This might be a central site, it might be unique for every project. The point is that we do not need to do the decommissioning at the site of production. The nuclear decommissioning can be done in a designated facility where such can be done in a safe and efficient manner. That is, of course, a difference to conventional nuclear, and we believe this is an attractive feature for the power barge concept as well. Yes, there is a comment in the chat box. There's both the point about the deployment in an island country like Indonesia, and we also see that, of course, it's the relatively small size of the 200 megawatt reactor is good for smaller energy systems, and the bar structure is good both because it has a very limited footprint on land, and it is of course easy to transport a full system to an island when you are already afloat. And then the question is, well, to what extent Indonesian components can be part of the product. And there we are continuously working on including as many local suppliers as we can. But there's also a trade-off. We believe, and that part of our key value proposition here is predictability and speed of deployment and cost. And these elements are challenged if we, for every project, develop a new supply chain. So we are building the product based on an assumption that we will have a very standardized supply chain across multiple deployments. Some of that supply chain could very well be Indonesian, but we are not likely in the first years to make specific component choices for specific projects, simply because it would jeopardize the timeline and the quality of the product too much. That said, there is a large scope outside of the nuclear barge also. Both there is the onshore facilities, the onshore substation, the onshore cables, and there will need to be a port or at least a key-like structure built where the power barge can be moored, so have its permanent location. So these construction works, they will need to be local and will be logically based on local supplies. And that's not an insignificant scope. And then lastly, of course, there's the long-term deployment and operations of the barge, and there is a large need for a skilled workforce, and there will be a lot of services around the operations where we will rely on local supply chains. So I hope that sort of answers it. So most of the key components within the barge will be standardized, and maybe they will be Indonesian, but not because of deploying in Indonesia, but because Indonesia would be these suppliers would be our global partners, and others will be from Korea or Denmark or wherever the better supplier will be for our global deployment strategy. Thanks for the question. So back to the life cycle here. So after 24 years, taking away to a decentralized centralized decommissioning site. And then the last slide that I brought, since our fuel cycle was also part of the topic for today. So this is how Seaborg envisions our fuel cycle for our uranium-based molten salt reactors. So there is, of course, mining, conversion into UF6 ultimately, and then enrichment. Our reactor runs on HALEU, so high SA, low enrichment uranium, with an enrichment below 20%, but also above 10%. So, but still in the classifications of low enrichment. That is then converted back to UF4, and then it is mixed into a salt. So this in step 5, that is where our fuel salt is created with the composition of salts and other minerals that we find ideal for our reactor concept. And then that uranium stays in the reactor for 12 years, as said. It's drained to in step 7. That's the draining to the drain tanks, where it can sit and rest and cool off until dragged out for the decommissioning. And this is where there is we believe that the industry should converge towards a a reprocessing element. The logic being that since the fuel is already a salt, that salt is easy to work with from a reprocessing point of view. There is no need to open and crack the ceramic uranium pellets. This is already dissolved in salt and ready to be processed, making reprocessing easier. And the overall ecosystem from a uranium point of view will benefit from this, and also reducing, of course, the radioactive waste volume substantially could this be done. That said, some of it will not be reprocessable. This is also some of the activated materials around the reactor core and so on, and these will need to be taken to a disposal and stored until safe to be reused in other ways. The vessel structure itself, as mentioned, will not be activated by radiation, so the vast majority of the steel structure, the electrical systems, the generators, and so on, we believe will be recyclable as any other vessel and industrial electricity system will be. And that was the last slide I prepared. Thank you very much for your time, and I hope we can then spend the remaining of the time with some questions and answers.
Okay, thank you, Nikolai. Before we move to the questions from the chat box, I think you've answered a little bit here, a few questions from the chat box, but we have two colleagues here from the university. We hope that he can give us also another perspective or another proposal for you as well, probably, because they also doing some kind of research as well for the molten salts. We have two colleagues here. The first is Dr. Siddiq Permana. He is the associate professor from ITB. This is the famous university in Indonesia. I think what is the ranking, Siddiq Permana, in the world? Part of the 200 QS World University. And also we have Mr. Azizul Hakim. He's also the researcher from Center for Reactor Technology. He's also doing research for molten salt reactor. For the first opportunity, I would like to hand over for Pak Siddiq Permana, Mr. Siddiq Permana, to give a response or comments or probably questions.
Okay. Can you hear my voice?
Yes, we can.
Okay, good. And I prepare some slides, actually too many slides, but I will keep the in short by slide, so can keep the time. So I will give response to Seaborg technology, but before I coming to the Seaborg technology, maybe I will I want to have another perspective, maybe some other enrich knowledge according to the small and modular and also the compact type technology around the world, that we can have the map and also the perspective related to the Seaborg technology. Okay, this is this is I'm belonging to the nuclear physics, biophysics group. So I'm also belonging to a graduate program and nuclear science engineering and also the physics, and also in the Faculty of Mathematics and Natural Sciences, and also the Center of New and Renewable Energy in ITB. Okay. Yeah, as part of the definition, so we already SMR, but the SMR is a kind of the definition, and it's a bit depend on the belong to the modularization or the power small or medium, and also the power small, medium, and also the modular. So that's why the range of power and also the range of modularity is become different. The IAEA try to make the classification, and the Seaborg is becoming the SMR, the whatever SMR, so small modular or small medium reactors. Okay, in the this is the statistic from 55 to up to now. So the compact reactor and the small the small reactors have been developed a long time ago, before 70s, and upgrade the power began 1000 early 70s up to now. So it's not quite new about the power generation, but modularity is different cases. And in terms of statistics also from the IEA, the SMR, small and medium, is about 40% actually has been developed and also operated in the world. So in terms of the small power, it has been divided into definition like SMR step 20 to 30, and also the very small less than 20. So this is belong to this definition in the presentation of IOP in 2016. And the view of US DOE about the benefit based on the SMR, modularity, and the investment is become lower because it's lower power and also the infrastructure, and also the flexibility of site, and also the efficiency getting better, and also the term of non-proliferation. And the other benefits, it can be built up multiple, and also can be used the existing license site, and also the reactor can be built the limited electric grid, remote area or island, such as Indonesia archipelago countries, and also become simple. Yeah. And this is just an example. Maybe we can see another perspective, land-based just for base reactor. So I just show here for the SMR, the integral power in terms of the power, thermal and electric, and also the size of the reactor pressure vessel, the core height, and also the primary circuit can be natural, and also the force convection. And the construction time for the reactor power, we can see from the Japanese history, NPP industry. So we can see for the low power generation or small power, we can see is around 2 and 4 years instead of the bigger power, BW and PW. And the other claims construction time for the SMR concept, it's around 2 years to 4 years for the current SMR concept. And also this is the variation of pressure vessel if we use the power output, and we need some pressure vessel diameters. In terms of economy, small become expensive, but if we try to reduce by modularity, and also the compactness, cogeneration, and also the grid stability, and the serial fabrication component, it can be reduced drastically by the learning curve, this modularity factor, design simplification, standardization also come into harmonization. So from this price, jump into a lower price, and face to face with the large reactors economic scale. This is a kind of the benefit for microgrid and also the process heating. And the size compactness, I just stick on this APZ for the emergency planning zone. So because very low for and also the inventory become lower, so the side boundary FEZ become very, very low. And another benefit is reducing the plant risk. So from the 10 to -5 up to the less than 10 to -7, or maybe in this design it can be reached 10 to -9 because of this modularity and also small power. And some other cogeneration, maybe in the next production for the seaboard, not only for the electricity, but also for the seawater desalination, as well as higher degree C for the thermochemical hydrogen production. And also we can see the benefit for small modular reactor. We can see integrating with renewable become the load following strategy. Up, down, intermittent condition can be followed by this strategy for the nuclear reactor as a load following technology. And yeah, this is example for the land-based SMR for the small multiple unit and become the compact and also base load technology. Yeah, not only for the energy ability, SMR also can be seen as the economic aspect, environmental aspect, as well as the social impact. And also we can use the all the cogeneration as a special energy utilization for the industrial complex supply, as well as for the desalination program in Indonesia also as well in current PLN program. Okay, this is, you can see actually from this book, I mean the tech doc from the IEA, there are 6 categorization for the small modular nuclear reactors. So this is the 5th categorization of Seaborg can be seen here in the molten salt small modular reactors. So if we take a look at a map, so this is Indonesia. We have a RDA, reactor daya experimental power reactor, and also Torcon. And also in Denmark, this compact molten salt reactor, and also CAWB. I forgot the abbreviation. And also this is the private sector and also government sector. This is the Seaborg from the European United Kingdom and also the Russian Federation. And also in Asia, we have, this is Batan, so now become Brin, yeah. So it still exists in this book. Maybe later on become a Brin, I don't know. And this is SMR design technology across the world. And also the time deployment, 2020. Maybe I see in the some slide, the Seaborg will be in operation. Sorry, licensing will be received 2025, and also the in the commercial 2028. I don't know, maybe can be explained later on. So this is as a comparison for the advanced reactor or generation 4 reactor. SMR can be seen here the time deployment by 2020, maybe some revision because of the COVID and some delay construction. And we can see here, this is the stage of design. So RDE, experimental power reactor in Indonesia, the small reactor, this is our output capacity in categorized as the conceptual design. So so yeah, I don't know in this book MSR, this is MSR, right? Maybe it's from this conceptual become the detailed design for the Seaborg. And also for the the land-based, or this is a land-based. You can see here a lot of land-based technology. And also for the marine-based, yeah, this is the KLT-40, it's already in operation now. And also the HTGR-SMR, so one of them also is in operation right now for the commercialization. This is a neutron spectrum SMR, and this is the molten salt. Let's see. This is one. This is a MCSFR or CA waste burner, belong to the Denmark design. Okay, this is a micro reactors. So the innovative reactor for the compact MSR is the moderator replacing the graphite into hydroxide, sodium hydroxide. The similarity with the LWR, it has the I don't know the material of this one, the stainless steel or no. This is something like cladding, but the fuel is liquid, and outside this fuel pin or fuel whatever we call, this is the moderator. Yeah, moderator fuel. Yeah, the moderator try to make it not in graphite because yeah, complicated change with iteration. Maybe from the high temperature reactor is a different fuel. Yeah, not complicated, but maybe need more innovation. And also some other the difference between this MSR compared to the other MSR with the graphite technology. And also there are alternatives overcome the graphite challenge. So the approach of Chinese, the pebble bed, this is the graphite tube, and yeah, non-moderator fast reactor, or adopt novel moderator material. This is the way of Seaborg, the four alternative, I think. Okay, yeah, the challenging is still in there, corrosion material concern, and also the neutronic performance because of low economic performance of hydroxide compared to graphite. And this is the comparison. So in terms of size and also the power output, this is the Seaborg, this is a new scale, this is the integrated MSR, and also the Westinghouse. Okay, yeah, this is right now been doing in the Seaborg related to nuclear module assemble, testing, educated, and economic scale, as well as in cooperation with the UK study, and also for the other research center for development of this technology. Yeah, this is I took this slide from this reference, also coming from Seaborg. So it's maybe it's more technical, but the important part is we can see here. This is the cogeneration with this Seaborg. So I just promote also Seaborg can be seen as the water desalination, and also the ammonia, and also hydrogen production and synthetic fuel, as well as the steam turbine for the electrical generation. Okay, I took this slide and see the thorium is 2050. So before 2050, you use enriched uranium or maybe trans uranium and so on. So in the end of the 50, you can use the thorium SMR, or maybe before as the nuclear waste burn. So maybe for the roadmap, you can more detail about this generation first CMSR, second, and also the third. Propulsion technology for this Seaborg proposal. and also for the, it's already mentioned about the employee. Okay, I see this is the supply chain set up for this Seaborg technology. So this is upstream, downstream, and also with the customer. But I cannot see here for the fuel cell facility. Is it in upstream? Yeah, upstream, or maybe in some part in between, or fuel cycle, because fuel cell in another technology, and also combined with fuel cycle. You see the closed cycle, you in your presentation, closed cycle is very important also, but another innovative technology, because a fuel cycle based on salt fuel technology. So you can consider also this facility or in between here. Yeah, this is the commercialization. We can see this is the license to operate. I hope I'm not repeated the slides. So I take this slide from this Seaborg publication, 2025. The license, I think this is license to operate. So it's already received in here, 2025. And for commercialization, the 2027 or 2028, maybe. So yeah, this is serial production and so on. And this is the funding, yeah. Okay, this is the floating utilization shipyard, turnkey delivery, movable asset, and also the remote communicating, and also in a special mining operation in the beginning. Yeah, Indonesia may be one of these remote, I mean one of the commercialization part. Yeah, it's a technical point of view. Although this is should be clarified, this is the, yeah, this is too technical actually. This is the pin gap, or this is the pin pitch diameter, and the very high optimization is compact, but you know, bigger pin also has a bigger irradiation from the fuel, and also the thicker of this cladding also can be seen also for the gradation cladding, and also the high temperature, and you know, this is the inner side is from, and the outer side from the corrosion of, or the reaction from the hydroxide. So maybe it's good news for the researcher, become innovative technology. Because yeah, up to now, usually the technology, high temperature technology, or the molten salt technology for the thermal reactor using graphite, but nowadays it's become, I think this is the stainless steel, or I don't know, the zircon, or I don't know, maybe can explain later on. Okay, this is the fuel cycle. So you use this natural, enriched, and also the spent fuel. And the end of this one, so you will use the thorium, and and also process and burn the waste. But the important part, you will lose your burn up, because thorium kept the absorb the neutron. But when you have the uranium-33, so the economy become better. So yeah, in this part is you want to reach, but this part your burn up become reducing in the economic point of view. Okay, this already mentioned, and also is already mentioned, but you can see here 12 years fuel cycle. You mean only fuel replace, or all the dock, I mean the can replace with the new one, and then replaced by the new one, or only fuel. So you can see this is which part is replacing, or all part is replacing in 12 years fuel cycle.
It's a full new reactor with fuel and drain tank. So it's a full reactor replacement.
Oh, okay, full facility in 12 years.
Yes.
Okay, So you remove all and then
We
replace
leave it
by
in
the
when we
other
use
part
it.
of this ship, right? Okay,
I'm
so
very sorry,
24 years.
And I'm sorry to interrupt, but I was actually told, or we scheduled this call to be an hour, and there are other things pressing
Okay,
me.
sorry.
So if we can round it off soon, it would be very good. Thank you.
Okay, this is already so.
Thank you, Nikolai.
Yeah. Okay, okay, I end up the presentation. Thank you. If you have any questions, let's discuss later. Thank you.
Thank you, Pak Siddiq. Thank you, Nikolai. You have a lot of questions actually, Nikolai, from the audience in the chat box. Yeah. But before the questions, probably Pak Azizul Hakim, we still have Dr. Azizul Hakim right now. He's also the researcher for Molten Salt Reactor. Pak Azizul, we use. Do you still have time for us to discuss the question on the chat box, or is that okay for you?
I will have 5 minutes more, but then I
Hello?
also have to attend another call. I'm very sorry, but I wasn't aware that we were to spend more than the hour.
Okay, so because we still have Azizul Hakim right now, is that okay to give his presentation a little bit, perhaps, Pak Aziz? Just a few for Mr. Nikolai. Mr. Aziz, please.
Okay, thank you very much. Maybe I will not. I didn't prepare any presentation, but I just make some note based on Mr. Nikolai presentation. Probably I will just share my notes on, and maybe some question also based on your. Can you see my note? I hope, yeah. Yes, it seems to me that your design is quite impressive to me, because you introduce several interesting features in your design. At least I can make I can note at least 3 features that you introduce in the design, such as the introduction of new concept of moderator, which is normally molten salt reactor is moderated using graphite, and it has also some challenges dealing with the graphite, and you introduce a new concept, which is sodium hydroxide, and this is a floating NPP. This also addressing new challenges for countries like Indonesia, where earthquake is very prone, and also follow-up event like tsunami should also be addressed in your designs. And also you mentioned that this design will be commissioned in the manufacturing country. For instance, if you manufacture the reactor or the ship, the parts in the Korea, and then you will commission in Korea, and then you move the reactor to Indonesia, for instance. And there I have several regarding your presentation, such as we know that fuel sat is normally very corrosive, and the question is then how do you address the integrity of the fuel tube, and what would happen if the fuel and moderator mix together due to rupture? And this question also has been addressed by Mr. Winters in the chat box. And number 2, I think you have addressed this question: how good the sodium hydroxide as compared to the graphite? And another question is how long that you will use sodium hydroxide, whether it is for 12 years, or you can use it for another 12 years, or and number 3 is how do you cool the moderator to receiving heat from the fuel, because the moderator is separated by the tube, and this will receive the heat from the fuel due to fission reaction, as well as gamma heating and also neutron heating. So you have to cool the moderator. And how will you cool the moderator? And number 4 is I think you already addressed the fuel drain tank under the reactor core, and whether it is whether it serves as a second shutdown system. But unfortunately, you didn't mention the first shutdown system, for instance, control rod or whatever. This is also very important in terms of safety feature. And number 5 is how the fuel management works, especially the fuel, and do you apply a feed and bleed system like other molten salt reactor, and what put up level are you is your limit, whether you're going to use the fuel again for the next step, or just for 12 years. And number 6 is you mentioned that IAE publication is your reference for your designs, and as we already know that IAE publication are mostly targeted for LWR. So which IAEA guides are you referring to regulate the MSR? And is there any country having developed the regulatory framework for MSR? And in terms of provenance level, how do you convince the targeted countries that your design has been proven? And are you going to build a demonstration plan prior to the commercial ones? I think you already addressed that you're going to build a prototype plan in this case. And has your design been verified for expected maximum earthquake and tsunami level? Because as we already know that Indonesia is very prone to earthquake and tsunami. And the last, I think it's already addressed by Mr. Sidik, what kind of other applications besides generating electricity, for instance, hydrogen generation, desalination, or maybe MO99 removal for medical isotope applications. Thank you.
Well, thank you, Dr. Azizul Hakim. Nikolai, for your informations, Dr. Azizul Hakim he's former of our regulatory body officer over there in Indonesia. That's why you probably see his questions very detailed and touch the, let's say, safety here and there, and also he also tried to figure out what is the applicable of IAA, let's say, regulation for the Seaborg type of designs. Okay, I think I'll try to highlight again the first question in the chat box is from Mr. Asin Sidki.
Mr. Bari, yes? I'm very sorry, but I have to tell you that now I'm also running the 15 minutes I gave you more. I think I read through both Mr. Azizul's very relevant questions, and I've also what is in the chat box. I think there are a lot of relevant questions, both to the corrosiveness and the fuel moderator mixing. And these are, of course, also part of the research program we have to make. Seaborg has to comply with an international safety case as any other nuclear system, and these are part. And honestly, not all of the research has been done to the extent that is required to make the safety case. We can, of course, make some initial comments, but we are not there yet. Then we wouldn't be in full commercial operations. I also have to say that the thorough answers of these is very long and time-consuming answers to provide, and they are better suited for forums with less than 80 participants, and some of it is export controlled, and most of it needs to be answered by specialists and not me. So I really welcome all the questions. I think they are great and correct. And they are also part of the reason why Seaborg has reached out to Bryn and Barberton, because we would love to engage in this dialogue, and we would also love to work with the universities in Indonesia to both increase the knowledge and to work together to find the new knowledge. But I don't think it's the right time and place here to provide the full detailed answer to all of these, part of which is because we are prohibited from it. But I think I would really welcome that we set up a future collaboration where we then, in the relevant for us, dive into these questions and matters in a relevant way. So instead of diving into it, because they are very, very detailed, some of them, and it would take me an hours to reply in a thorough and meaningful way. So I would rather that we take that bilaterally in some other more targeted meetings than in this more generic focus group, if that's okay with you.
Okay. Okay. Thank you, Nikolai. I would like to give a little information again. We have friends from utility company, from electricity company right now. Perhaps outside the questions, they probably have a concern from how to really deploy the molten salts, compact molten salt reactor. We have Pak Sugeng here. He's from PLN. Pak Sugeng Triyono probably would like to give some comments, or and what especially from Mr. Asin Sidki. If you see the question chat box, he was the president of the chairman of Indonesia Power, the former of chairman of Indonesia Power, and Mr. Asin Sidki is from the electricity company, right? And Pak Sugeng, ada pertanyaan tidak? Pak, mungkin, atau teman-teman dari PLN, silahkan mungkin. Because we invite our colleagues from PLN, from SDM as well, the Ministry of Energy and Mining, to give comments of just try to engage with you, so we can have further collaborations, more or talk about what is the opportunity for them to deploy, or to let's say to contact you and give the understanding of what is the technology of Seaborg here right now. Pak Sugeng, mungkin ada teman-teman dari PLN, silahkan. Nah, nanti saya translate coba. Are there any particular, or if it's not, are there any particular research would you like to highlight, Nikolai, or propose for collaboration with Bryn? Because we have here Mr. Rohadi Awaludin. I'm hoping that he's still right now in our Zoom meeting and for focus group discussion. So we will understand what kind of joint collaboration, let's say, or whatever, between Bryn and Seaborg in the future.
So there's, of course, a lot of relevant questions that we can work on. I think, which has also been proposed by Mr. Jarrett. From Seaborg's point of view, we think that there is a very relevant, given the rich resources in Indonesia, in particular in the uranium space, to work on the fuel supply chain together. There is a lot of research still to be done within the both the upstream part of the fuel supply chain, so from mining to molten salt stage. But in particular, there is work to be done in the reprocessing and waste management part of molten salt. And from Seaborg's point of view, we believe that this is one that would benefit the industry and Indonesia, regardless of which technology provider ultimately will provide molten salt reactors to Indonesia. So we think this could be a good area of collaboration. in terms of our molten salt reactor itself and use of sodium hydroxide as the moderator, this is Seaborg's proprietary technology, and this is our commercial existence that depends on this. And therefore, we are hesitant to engage in too many broad collaborations around the co-development of that technology. Should there be specific areas which is of relevance, we are of course open to discuss, and we will really like to share and co-understand together with BRIN and relevant authorities in Indonesia, of course, so that it is something you can be comfortable deploying by the end of this decade. But that would be under less of a co-development heading and more of an information sharing, which of course is bound by other confidentiality restrictions. So, but that said, I think the fuel cycle is one, both upstream and downstream, and the decommissioning side. I think those are very relevant topics to be dealt with from a research point of view, and in particular for Indonesia, given the uranium already in Indonesia.
May I confirm something, Dr. Seaborg, to
Yeah.
collect?
Yeah.
Thank you. I just mentioned about the slide before, so about this one. So the original one is 100 megawatt electric, and 200 means you multiple. I mean 2 units, 100 and 100. Is that right? Or you just made another type, bigger power?
It's two.
Multiple, okay, 2 types, as well as 400 for multiple units, and also 600 for 6. That's the strategy, right? Not constructing the new, the bigger power density or something like that.
Correct.
Okay, just multiple. And one more about the cycle. This one. So in your, let's say this is the...
It's a relatively outdated slide, and I would love, Mr. Siddiq, I would really like to answer all your questions, but I also have to tell you that I have people waiting for me for 30 minutes now, and I'm trying to be patient with it, but I think we should round off as soon as possible. Could I just shared the presentation I've given today. On the last slide, you'll find my email. I welcome everybody who wants to have a further discussion to send me an email, and I'll be very happy to set up individual calls. I can tell you that this is not the latest information that is out there.
Thank you. So yeah, I just show you the reference. So 2019. Yes. So if you have any
3 years
updated information, you can share with us. Okay, thank you.
Yeah.
Thank you.
Okay, thank you. Nikolai, again, about the possibility for future for BRIN, let's say, involved in the research of fuel cycle, let's say, for example, sort of like that. What is your plan for, let's say, to localize the fuel fabrication in the future? Because we are in Indonesia, we have an experience for our research reactor. It was constructed in 1987, and then we've produced. We start to try to get the technology transfer in terms of how to manufacture our own fuels, and then we successfully localized our fuel fabrication in 1995, if I'm not mistaken. Yeah. So, is there any possibility from Seaborg, sort of like that, to try to have technologies transfer in the future and try to localize? Because if it's the reactor is only one, I think it doesn't matter for Indonesia. We just imported the fuel, and then after that send it back, everything to let's say to vendor, sort of like that. But for us, if it's more than 5, for example, let's say I think it's more economic for us to develop our own fabrication. We've seen here that the technology seems not really complicated compared with the PWR. I'm not sure, but probably you have a plan for whatever country would try to deploy the NPV, because this is our concern as well as a research organization try to adapt with the kind of technology.
So also that is a long question, 30 minutes after deadline, but I think it's a good, but it's a good one. So we are not, Seaborg is not active in the fuel supply chain. So we are not a fuel manufacturer. We expect to buy that from a third party. So to that extent,
right.
we are not the ones driving the localization of the fuel supply chain. But on the other hand, it also means that we are not bound by our global supply chain approach, which relates to the barge manufacturing. We as a company have the view that it would make a lot of sense because we think Indonesia has a great future for nuclear application, and you have uranium in the ground. We believe that it would make a lot of sense if Indonesia has an active role in the full fuel supply chain. But as we are not the ones with the primary competencies and who will not be the ones actually making the investment decision of setting up a fuel supply chain in Indonesia, we cannot drive that alone. We would be very, very happy to engage in the research around and the development of the concept as to how Indonesia can be a key player in the molten salt fuel supply chain, but we are not the only ones driving it. So that I think that's the short version of it. We would really like to take in our fuel supply chain collaborators and bring them to Indonesia and have that wider discussion when the time is relevant. I think the starting point is to say that BRIN, on behalf of the Indonesian government, if you will have to do some research into the fuel supply chain, and there needs to be a strategic decision from Indonesia as to in what part of that value chain would Indonesia like to have an active role. And once that is defined, we can then work with the experts and the vendors in the fuel space and work on a localization plan around those areas of the value chain where Indonesia would like to be active. I think there's a lot of elements that are outside of the control and decision of Seaborg, but we will be very happy to contribute with whatever we can to inform BRIN so that you can make the proposal to the Indonesian government so that Indonesia can play the role in the value chain that they would like to.
Oh, okay, good. Thank you so much. And another one, I'm still curious about the licensing actually, because I've seen that so many nuclear power plants in the last era, I think, they increased the cost because of licensing. The cost is just come up because the license just comes with the new idea, especially with the NRC, the new idea, then they need kind of this component, so the cost is increased, the fuel is increased as well. And as well as the certification of fuel, the quality of certification of fuel also, yes, it becomes so complicated right now. Yes. What is your view right now? For example, in terms of how to deal with the regulations, how to certify of your fuel right now, and to still keep your price below your competitor, let's say, coals or other PWR.
Yeah. So I'll keep it brief because again, that is a full day's discussion. This one, I think.
Yes.
I'm very sorry to dismiss most of the questions. It's of course a challenge that we are aware of, and that's a very significant part of our work is around our licensing, both in terms of the plant and the fuel, and working with the authorities, both in our developing the countries where we develop the technology, but of course we will also be working together with the authorities of Indonesia to the extent we want to deploy in Indonesia to try to mitigate these key risks that you mentioned. Okay,
and the last, I think, from me about the waste, I think.
And could we please also agree that that is the last question?
Yes.
Thank you.
Okay, no worries. Yeah. About the waste, I think you've mentioned that it seems that from your presentation, there's no waste produced for the, let's say, for the fuel, spent fuel, sort of like that. Is that true, sort of like that? Or do we need to another research to be prepared right now in for BRIN in the future, for example, if we want to deal with this kind of technology?
So I'm not sure I understand the question. There will of course be there will be spent fuel, and there will also be waste. There will be non-productive isotopes in the fission products that will need to be dealt with as waste. I think that's the short answer. And how that is dealt with, and also in particular in Indonesia, I think that is part of this fuel value chain question relating to the decommissioning and waste management of nuclear reactors. And I think our fission products will be very similar to those of any other potentially proposed molten salt reactor deploying in Indonesia, and therefore I think it's not a Seaborg specific research. We would be very, very happy to be the primary or maybe only partner in the research, but I think it's of benefit to Indonesia regardless of whether Seaborg deploys barges or you get molten salt reactors from one of our colleagues in the industry.
Okay, thank you so much. Yeah. Okay, ladies and gentlemen, I think that's the last question from me as also from the participants. Nikolai, if you don't mind, I'll try to collect the questions from the audience, because this audience are really curious and would like to understand what kind of technology of the Seaborg. We don't want to buy something that we don't understand at all. Of course, that's why we need to start the communication with understand each other, and as much as we know what is the current status, how to prepare the research for us, and how to prepare our human resources for us. Whatever the government asks us, is that Seaborg is good? Is that Seaborg is appropriate for Indonesia? I think we can try to answer. We can try to help them as well to answer. And our regulatory body also, they also ask us, our university and our institution, as the technical organization as well, sometimes, or the vendors or whatever comes to Indonesia.
And we really appreciate this opportunity to initiate the dialogue, but I also am of the opinion that this cannot be the only interaction. So I am comfortable that there are questions that are unanswered, because some of them will be answered through a very long and close collaboration between the bodies in Indonesia and Seaborg. So we would very much like to participate in follow-up calls, focusing in on some of the specific questions. I think we had too little time to get around all the very, very good and relevant questions today, but we would be very happy from Seaborg to set aside time, and we would bring in the specialists. Should there be specific questions that needs to be answered, then I would much rather than me giving a generic answer, bringing in the specialist and maybe even forming the relevant collaboration between Seaborg and the relevant parties in Indonesia to actually get to the depth of it, instead of me answering superficially within a very limited time. So
okay, great.
I hope that is appreciated.
Oh, really appreciate it, Nikolai. Really appreciate. Yeah, thank you so much. And anyway, do you send some kind of collaboration agreement to BRIN?
I've shared with Mr. Jarrett an initial proposal for the scoping of the work, and it is with BRIN, but we are open to whatever BRIN prefers, and also we would like to engage in that dialogue in more detail.
Okay.
But I propose that we do that bilaterally.
Okay, good. Because we open to all vendors coming to Indonesia, and we hope that yes, we are neutral with the technology as well, and our aim is just would like to get the first nuclear power plant, whatever whatever type, and we can try to have a good collaboration as well in terms of research, how to really prepare the first nuclear power plant, good for Indonesian, good for you as the vendor as well, and good for the nuclear, for the world, as I think. Yeah. Thank you so much. See you next time, Nikolai. Yeah. Thank you so
everyone.
much. Ya, bye. Bapak Ibu sekalian, terima kasih atas. Sorry, I'm trying to close with bahasa Indonesia to other audience. Bapak Ibu sekalian, terima kasih atas perhatiannya. Mungkin ada beberapa pertanyaan teknis yang tidak bisa dijawab, yang tidak mungkin dijawab dengan beliau begitu. Nanti kita simpan saja, kemudian kita kirim. Saya berharap sebenarnya ada diskusi teknis tadi. Saya mungkin ada keterbatasan satu atau dua hal, mungkin dari Pak Sidik. Mohon maaf ini.
Saya pengen share sebetulnya tadi, tapi
Aziz, ya, oke, nggak apa-apa, ya, nggak apa-apa. Nanti kita akan undang mungkin pada saat mereka ada di di Jakarta begitu, sehingga dia akan berjanji akan menyampaikan pertanyaannya begitu, pertanyaan Bapak Ibu semua, dan juga sekaligus mungkin mengundang engineer-nya begitu ya untuk menjawab. Wah, ini susah-susah ini pertanyaannya Pak Aziz ini sama Pak Sidik. Nggak apa-apa, bagus. Saya terima kasih Bapak Ibu, thank you so much semuanya. Tetap sehat. Terima kasih Pak Jarod sudah membantu menghubungi Pak Nikolai. Mudah-mudahan nanti
Kaget juga ya, pertanyaannya banyak.
Iya.
Pak Saiful nggak membatasi, jadi saya tanya apa aja.
Oh, yes. Saya memang berusaha untuk mengorek mengorek sebanyak mungkin begitu kan, yang bisa kita dapat begitu kan. Soalnya dicari di publikasi itu udah ketemu itu Pak.
Saya dapat yang ini Pak, beberapa Pak. Publikasi
ketemu di publikasi begitu. Bapak Ibu jangan lupa aksennya ya di. Ya, agak susah ini. Padahal kuncinya di fuel, dan kalau secara kimia begitu ya kami nggak terlalu paham masih, karena riset kami masih jauh. Dengan Torkon aja nanti kapan-kapan mungkin minta tolong Pak Jarod juga ngundang Torkon ini.
Ya. Mungkin Torkonnya kita undangnya si dari Amerikanya juga.
Sila juga. Mungkin offline mungkin di mana kalau bisa offline di Serpong lah, di gedung 20 Pak. Oh ya, jam 20 apa?
Tapi langsung jarang ke Indonesia sih, kadang aja sih.
Iya. Kan pengennya kita juga tahu risetnya mereka seperti apa, statusnya seperti apa.
Skema bisnisnya investornya apakah tetap perlu dari kita atau mereka bawa sendiri gitu? Atau dari mana investornya gitu kan? Kan venture ya. Awalnya 2014, terus kemudian berkembang, punya desain, punya ini. Terus kalau bisa ya dipatenkan di kita gitu kan, punya teknologi.
Iya, masih banyak bolongnya. Dia bilang kan, wah saya lagi ngerjain ini. Wah, ini Mas Aziz aja bisa bikin gambar kayak gitu, sama itu. Ini lagi ngerjain ya Mas Aziz.
Kesempatan dengan BRIN Pak.
Iya. Kayaknya mintanya sign up MOU dulu ya Pak Jarod ya kayaknya.
Oh iya, NDA macam-macam ya.
Padahal lama sekali itu MOU dengan BRIN itu. Ya. Tapi nanti pertanyaannya mohon mungkin nanti gagat untuk mengkoleksi, nanti kita kirim ke Pak Nikolai.
Iya. Apalagi pertanyaannya Mas Aziz langsung keder bener. Pertanyaan
langsung cepet-cepet selesai.
Regulatori.
Udah saya share di chat itu.
Oh iya, kasih Mas Aziz.
Jadi harapannya nggak apa-apa juga sama beliau.
Ya, tapi nggak apa-apa. Dulu pada saat DSNS datang ke Serpong juga ya kita tanya macam-macam juga begitu kan. Ya keringetan juga mereka. Padahal sudah bawa expertnya ada 5 atau 6 orang saat itu. Saya ingat masih di gedung 80 gitu. HTTR juga sama dulu begitu datang Jepang. Ya kita tanyakan.
Kalau pengamat itu lebih ahli biasanya.
Iya.
Jadi daripada bikin sendiri.
Begitu sudah ngeriset ya kita masih jauh. Bapak Ibu terima kasih Pak Jarod, terima kasih Pak Sidik. Bapak Ibu jangan lupa diisi absennya. Selamat sore semuanya, salam sehat selalu. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. Izin saya end semuanya. Assalamualaikum.
Ya, terima kasih Mas Ade.